Will Mars be the next step in our exploration and exploitation of outer space? Find out on an Everyman's Guide to the Planets next from TLC.
Man's fascination with the planets has been with us since the first humans looked into the sky at night and attempted to understand the points of light which moved about seemingly on their own. Until the development of sophisticated telescopes, the only planets which man knew of were the inner planets, Mercury, Venus, Mars, and two of the outer planets, Jupiter and Saturn. Of these known planets, Mars has probably held the most fascination for us. Early in our study of this planet, it was believed that the god of war lived there, hence the name Mars. Later, when early astronomers discovered what they thought were canals on Mars, they theorized that an alien civilization lived upon the planet. Aliens who carved out vast waterways to bring water from the poles to quench a desperate need for the life-giving liquid. In many ways, the beliefs held by these astronomers about the mysterious red planet were caused by an intense desire to find some other place in the universe that was like our home, the Earth.
And what of the Earth? Earth, the third planet in our solar system, is located an average of 93 million miles from the sun on a nearly circular orbit. It is currently tilted on its axis 23.5 degrees. I say currently because we know that the Earth's tilt can vary by as much as 2.5 degrees over a period of 40,000 years. This fluctuation in the tilt of the Earth could be what accounts for the past ice ages which have occurred on our planet. Periods of history where huge glaciers have covered much of the land mass present in the world. The last such ice age ended only about 10,000 years ago.
The Earth itself, as well as most of the solar system, is about 4,600,000,000 years old. We know this from scientific dating of rocks and meteorites which have fallen to Earth. As old as that may seem to us, it is relatively young when you consider that the age of the universe could well be hundreds of billions of years.
But how does the Earth compare to the other planets? As you can imagine, our blue planet is absolutely unique in many respects.
Were you an alien traveling through the solar system, let's say, on a tour of the 9 planets, the one remarkable thing you would notice about the third planet from the sun is its color, brilliant blue. No other planet reflects this particular color, which is due to the existence of water vapor in the atmosphere. Beautiful swirling white clouds give contrast to the blue of the oceans as they pass over the greens and browns of the continents.
Our atmosphere is made up mostly of nitrogen, carbon dioxide, and oxygen, with trace amounts of helium, argon, and believe it or not, krypton. The other planets in our solar system either have little or no atmosphere, or atmospheres made up of hydrogen and methane. The Earth's atmosphere is extremely tenuous. It extends to only 248 miles above the surface of the planet. We humans, and indeed all life forms that roam the surface, cannot live above 25,000 feet from the ground. Above that height, the atmosphere becomes so thin, our bodies cannot absorb enough oxygen to sustain life.
The atmosphere of the Earth is a place of constant change. The heating of the surface during the day and the subsequent cooling at night, along with the rotation of the planet, all work in concert to create a flowing dynamic pattern, what we commonly refer to as weather. Another thing you would notice is that unlike Mercury or Venus, the Earth possesses a large satellite, the Moon. It is the first planet in the chain of planets that make up the solar system to have one. The Moon, as it turns out, is absolutely devoid of any of the organic materials necessary for life. It is too small to have held an atmosphere for very long after its formation, and its pockmarked appearance tells the tale of billions of years of cosmic pounding by meteorites, some large enough to have melted the surface and thrown chunks of rock hundreds of miles. Unlike any of the planets in our solar system, men have been to the Moon. So far, only 12 human beings have walked its surface, bringing back invaluable data in the form of lunar rocks. These rocks reveal that the Moon, though created about the same time as Earth, was not originally part of the Earth, as many people believe. It is made up primarily of feldspar, potassium, iron, and magnesium.
There are currently no missions planned to return to the Moon. The last humans to walk its surface left in December of 1972. Should we decide to begin in earnest our human exploration of the other planets, there would be no better starting point than a base built on the Moon. We will return to our old friends someday, and it will help us unlock the mysteries of the universe.
The Earth's crust is not as solid as we imagine. In fact, it is broken into several pieces called plates, which float on a sea of superheated liquid rock known as magma. These plates are in constant motion, moving across the Earth's surface, carrying islands and whole continents with them. In fact, at the time of the early dinosaurs, about 225 million years ago, all of the continents as we know them were joined together as one huge mass continent known as Pangaea. We know this because we have found that several identical specimens of dinosaurs can be located on different continents scattered all over the planet's surface. Where these continents are separating one from another, we find huge amounts of liquid rock pouring forth from the ground, what we call volcanoes.
Now, where these continental plates are coming together, we find the ground pushed up to great heights, what we call mountains. It is important to realize that every mountain range, every hill for that matter, in the entire world has been formed by the movement of the Earth. Now, this movement of the Earth's surface goes on continuously, though the only time that we humans are made fully aware of it is during its most violent moments, and those times are called earthquakes.
In one particular case, the state of California is divided into two huge plates, the Pacific Plate on the west and the North American Plate on the east. The dividing line between these two is known as the San Andreas Fault. Unlike many fault lines that form the boundaries between other plates on the Earth, the San Andreas is known as a strike-slip fault. This means that the two plates are sliding against one another, the Pacific Plate moving north and the North American Plate moving south. Since the two are definitely not separating east and west, it is clear that the coast of California will never fall into the ocean, as has been predicted in the past. What is likely to happen, however, is that within 1 million years or so, Los Angeles as we know it will become a suburb of San Francisco. So great will its northward movement have been.
Mountains, volcanoes, and earthquakes aside, what makes our planet so remarkable within our solar system is that one property which allows us to discuss this subject at all: life. Nowhere else in the solar system have we found anything like what we have here on Earth. This planet is literally teeming with life forms, organisms of all sizes, from elephants and whales to single-cell amoeba. Life is found everywhere in the world. We found microbes in the ice floes of Antarctica, as well as sulfur-eating bacteria around the deepest underwater volcano vents. You simply cannot go anywhere on Earth without being surrounded by millions of different forms of life.
As far as we can tell, life began on the planet Earth some 3,100,000,000 years ago in the form of bacteria-like creatures. These bacteria were present all over the globe and lived in shallow pools of water. We have found their remains in rock dated back to that time. At about 2.5 billion years ago, the first complex organisms began to be found. These were mostly worms and jellyfish, once again, creatures which lived in the sea. It took several millions of years before the first creatures evolved with which we could identify today. Originally, these were the shellfish, clams, and mussels, then insects such as beetles and some spiders, then eventually fish, and most importantly, amphibians.
It is these amphibious organisms which quite literally crawled out of the prehistoric muck to live outside the ocean that would later develop into reptiles, cold-blooded lizard-like beasts, and mammals, warm-blooded animals like ourselves. For a while, a sort of half-breed, the mammal-like reptiles seemed to be the creatures of choice, the ones best suited for life on the lands of Earth. But then, 225 million years ago, a change occurred. No one is quite sure what exactly this change was, but it marked the beginning of the reign of huge reptilian monsters which dominated the land and the water. It was the time of the dinosaurs.
Dinosaurs lived on the Earth for a period of about 161 million years. 64 million years ago, nearly all of them became extinct. No one knows exactly why, but it appears as though the Earth changed in a significant enough fashion that they were not physically able to cope with these changes, and therefore they all died.
After the extinction of the dinosaurs, mammals became predominant, maybe because they were no longer being eaten by hungry dinosaurs. Anyway, these mammals continued to develop, and about 3 million years ago, barely a blink in the life of the Earth, our earliest human ancestors appeared. Now, modern man has only been on this planet for about 50,000 years, barely a single tick in the clock of the Earth. Yet we have progressed beyond any other organism which has preceded us. We are now in a position where we can change not only the surface features of the planet, but its atmospheric and chemical composition as well. No other creature has literally molded the planet to suit its needs as we humans have done. And no other creature has caused as much damage to the ecosystem of the Earth as we have.
We have an awesome responsibility to this planet. Nature has provided us with all that we need to live and prosper. Through our manipulation of the elements, we have altered the environment. Several species of animals have either become extinct or are nearing extinction due to the works of man. We have poured huge amounts of harmful chemicals into the air and water. We have cut down vast amounts of forest land to make way for human habitation.
Now, this may sound like a dismal indictment of our civilization. All is not necessarily lost. Though we have plundered our planet's many resources, we've also taken the time to study our world and to develop a better understanding of how it works. Already, movements are afoot to correct the imbalance which we have caused. We've launched space probes to study our planet and to observe the subtle changes which could spell disaster for our future. We have developed the means to either enhance the Earth's natural gifts to our advantage or to destroy that upon which we depend to survive. As we have seen, our world has the incredible capacity to be a delirious heaven or an unmitigating hell. It is up to us to decide exactly where we want to live.
Mars, the fourth planet from the Sun, after the third, which is Earth, is not nearly as big as most people imagine. In diameter, it is half the size of the Earth, about 4,213 miles. Although it is half the size of Earth, its mass, that is its weight, is only 1/10 of ours. Mars is clearly made of much lighter elements than our home planet.
Much has been made about Mars throughout man's history. It was named after the Roman god of war, appropriately, for it is the only object in the nighttime sky that reveals clearly a color, red. The ancients believed that the blood of men slain on the battlefield colored the planet. We now know that it derives its color from an abundance of hydrated iron oxide on the surface. Not very romantic, but scientifically more precise. Mars is dissimilar to Earth in many ways. For instance, its year, the time in which it takes to circle the sun, is 687 Earth days, about twice as long as ours. It does, however, have a day that is almost exactly the same as Earth's, 24.4 hours. And very importantly, it is tilted on its axis, almost exactly the same as Earth, which gives it a change of seasons, just as we have here, except for the fact that Mars' seasons are longer. The surface pressure of Mars is about 1/100th that of Earth, and the atmosphere of Mars is not very hospitable to human life. It is mostly carbon dioxide, nitrogen, argon, and a small amount of oxygen. Though it is insufficient to sustain human life, it is rather similar to the chemical makeup of our own atmosphere. Theoretically, you could breathe the air of Mars. There is so little oxygen in it that you would surely die within seconds of doing so.
The atmospheric pressure on Mars is equivalent to the atmospheric pressure you would feel at 100,000 feet above the surface of the Earth. So it's not likely that you'd be able to take a breath of it and survive.
Temperatures are not quite what you would call balmy on Mars either. During the peak of the summer on the planet, the temperature on the equator may get as high as 40 degrees Fahrenheit, but at night that would dip down to minus 140 degrees. Close to the coldest temperature recorded on the face of the planet Earth. Again, not a very bright picture for human existence on the planet. There is one thing we know that Mars has, however, that raises the most excitement when discussed. Mars has a substance that occurs naturally in great abundance and is invaluable to mankind. A substance which is not rare in the solar system, but is more precious than gold or platinum. Mars has water. Early observed the planet for hours on end, drew pictures of the planet with representations of huge canal systems running the entire length of the planet's surface. This is quite extraordinary, as we know that it was quite impossible for these early observers to see any kind of significant detail on the surface due to the limited optics that they had in their telescopes. Yet several different and notable astronomers drew these canals time after time. How they did it, no one knows. What we do know is this: there is massive erosion on the surface of Mars. Huge valleys have been cut into the planet, some with cliffs that stand 15,000 feet over their bases. Channels and estuaries cut into solid rock, all of which could only be the remnants of once great rivers and oceans of running water. So where did all the water go? Well, out into space, most likely. The atmosphere of Mars is extremely thin. So thin, in fact, that liquid water on the surface would boil away without heat, and ice would slowly evaporate and disappear. At one point in the history of Mars, there must have been enough atmospheric pressure to hold all the water in. But it's very obvious that there was a considerable amount of it on the surface of the planet. There is also evidence that seems to indicate that water in liquid or ice form still exists underneath the surface soil. And the argument in favor of that is right here. You see, all planets show signs of being impacted by meteors of various sizes. In the early formation of these planets, these impacts occurred with some regularity, hence all the craters on the moon. Earth was subject to the same bombardment, but since our atmosphere is so active, the wind, rain, and rivers washed away most of the remains. However, on dry planets with little or no atmospheres, such as Mars, these factors do not account for much erosion. Therefore, the craters are still there. But what does that have to do with water on Mars? Well, let's take a look at a typical crater and see how it is formed. A crater is formed when a large object, usually a meteor or asteroid, collides with a planet, or in the case of the moon, a satellite. As the meteor strikes the surface, it generally heats up the impact area sufficiently enough to melt the meteor and the surrounding rock. This then flows forcefully outward in all directions, leaving a crater in the center and a telltale spew of ejecta around the crater. In almost every case, the ejecta appears to be made up of melted surface rock and melted meteor, except on Mars. On Mars, much of the ejecta looks exactly like flowing mud. This then would tell us that Mars still has water, either in the form of flowing underground springs or as subsurface ice. In either case, we have a planet to which we can go and find that one resource that will allow us to live there permanently. With water, we can make oxygen to breathe, and we can grow plants and animals to eat. We can go to Mars and we can live. Mars, for all its strange beauty, is a veritable wasteland. As far as we know, nothing could live on its surface. There is no ozone layer to speak of, so deadly ultraviolet radiation from the sun rains down mercilessly on the soil. Surface temperatures anywhere on the planet seldom rise above freezing, and then only for an hour or two a day at the equator. At first blush, Mars would appear to be an interesting but dead world. Currently, there is much talk of a manned mission to Mars, perhaps with the Soviet Union and the United States acting in concert. One thing remains clear. If we put forth the effort, man can travel to Mars, can live there, even develop a civilization there. Water can do many things. It is the universal solvent of all life as we know it on Earth. With it, as we said, you can make oxygen to breathe. You can raise food. You can use it to feed plants, which will give off gases that will change the atmosphere of the planet to make it more hospitable to life. Our future journeys to the stars must begin with a base camp firmly entrenched on the planet Mars. Then, and only then, can we say that we have seen the Martians and they are us.
Travel millions of miles to the icy worlds on the edge of our solar system as an Everyman's Guide to the Planets continues next on TLC.
So far on our journey to the planets, we have encountered worlds that are made up mostly of rock, worlds that are shaped by the forces of geologic activity. We know for a fact that Mercury, Venus, Earth, and Mars have been shaped by both tectonic forces and by volcanoes. We also know that, with the exception of Mercury, all of the inner planets have an atmosphere. But what happens when we leave the inner part of our solar system and visit the outer planets? We no longer find planets that are made of rock. Instead, we find planets that are, in effect, total atmospheres. They are all, except for the tiny planet Pluto, made up entirely of gas. The outer planets are still worth our study, however, for many different reasons, not the least of which being the diversity of their moons, which, by the way, are solid. The outer planets exhibit weather patterns that boggle the mind. Some hurricanes on the outer planets travel at supersonic rates well in excess of 800 miles an hour. Yet even at those horrendous velocities, they behave much in the same way as hurricanes on Earth. The magnetic fields of the outer planets are so immense that in the case of Jupiter, over 1 million rads of radiation spew forth from the planet. That is over 2,500 times the amount of radiation needed to kill a human being instantly. Yet the magnetic field of Jupiter behaves much in the same way as Earth's. Thus, there is much to be learned from studying the gas giants.
So now we move on to a place of great wonder and mystery, a place which, as we speak, is under mankind's direct observation, a place which will one day be the way station on our journey to the stars. When we travel past Mars, we encounter an area known as the asteroid belt, within which are billions of chunks of ice and rock of various sizes. This seems to be either the remnants of a once mighty planet that was perhaps destroyed by a massive collision, or, most probably, an area where the junk of the solar system is gathered. In any case, it forms the demarcation line between the inner and outer planets.
The asteroid belt is a collection of small to medium-sized chunks of the types of materials that formed the planets originally. They're mostly rocks. Some of them are rocks mixed with iron. Others are rocks that have a high content of organic carbon-bearing materials. Current theories of the origin of the solar system suggest that it's basically leftover materials from the formation of the solar system that didn't get themselves into a planet and didn't get close enough to Jupiter to get flung out of the solar system, as we believe happened with many of the comets, which were perturbed gravitationally out to the outer solar system and now come back to visit us every once in a while as a result of perturbations from other stars.
Up until now, we have focused on the inner planets, Mercury, Venus, Earth, and Mars, all of which are rocky in nature and have atmospheres made up primarily of oxygen compounds. The outer planets, that is Jupiter, Saturn, Uranus, Neptune, and Pluto, are all, with the exception of Pluto, made up almost entirely of gas, and gas in a liquid state. All have atmospheres that are based on hydrogen compounds, and all, once again with the exception of Pluto, are absolutely enormous in size when compared to Earth. The first of the gaseous planets is Jupiter. Now, to say that Jupiter is large is to be guilty of an incredible understatement. Jupiter is enormous. By far the biggest planet of the system, it contains more mass than all the other 8 planets combined. To get an idea of exactly how large Jupiter is, witness this. The Earth has a diameter of roughly 8,000 miles. Jupiter is 89,000 miles in diameter. It is 318 times as massive as our planet and contains 1,300 times as much volume. Jupiter is formidable indeed. It is essentially a star that failed to ignite. If you analyze the chemical composition of the Sun and Jupiter, you find that they are remarkably the same. The only difference is that of size. For had Jupiter been larger by a factor of 10, it would have collapsed upon itself and lit, thereby giving us a binary star system, one where we would have had 2 suns in the sky. Life would be very different on Earth had that happened. But it did not. So we are left with a planet which is, in reality, a huge ball of gas with a liquid center and possibly a rocky core. Where the planet derives its distinctive coloration remains a mystery, but one theory stands out as the most plausible. You see, Jupiter exhibits the strongest magnetic field of all the planets, and as such, creates millions of lightning bursts per day. This, in turn, mixes and matches the molecules in the atmosphere to form various hydrocarbons, what we on Earth call smog. Possibly it is these differing hydrocarbons that give Jupiter its color. This also creates another intriguing possibility. As hydrocarbons are formed and burned, a waste product is created. This waste product is carbon, the most basic and stable element in the universe. Now, since carbon is heavier than hydrogen or helium, it would sink towards the core of the planet. As it sunk deeper and deeper, the temperature and pressure would be an astounding 1,000,000 times the surface pressure of Earth. Now, we have evidence on our own planet of what happens to carbon, which is heated to extreme temperatures and subjected to intense pressure. The carbon atoms realign themselves in the tightest, most orderly, most stable fashion in the universe. The center of Jupiter, then, may very well be a solid diamond, the size of the planet Earth. The planet rotates once every 9 hours, so the clouds are spread out as various bands. The most distinctive area of Jupiter that has been observed and formed the most speculation has been what is called the Great Red Spot. And it is just that, a giant red spot on the visible surface. Once again, we do not know why it is red, nor why it has existed for at least 3 centuries. However, it appears to be a huge storm of sorts raging in the upper atmosphere.
The Great Red Spot is essentially a very large weather system. Whether you want to call it a storm or a big high-pressure zone doesn't really matter too much. It's an exceedingly large weather system with the cyclonic pattern that we see in large weather systems on the Earth, huge hurricanes, typhoons, large high-pressure ridges, things like that. But as I mentioned before, it's larger than the entire planet Earth, and its size is one of the reasons it persists for so long. As far as we know, the Great Red Spot is effectively a storm on Jupiter that's been going on for 300 years.
And Everyman's Guide to the Planets will continue on TLC. And Everyman's Guide to the Planets now continues on TLC.
Io, the 3rd largest moon of Jupiter, is one of the reddest objects in the solar system, due entirely to its incredible amount of volcanic activity. It appears that Io is covered from pole to pole with huge erupting volcanoes, and is clearly the most geologically active spot in the system. This appears to be caused by the incredible magnetic forces emanating from its parent planet and that of its neighbor Europa.
Io, the satellite of Jupiter, has active volcanoes on it. It's a very hot planet, and the source of that heat is interactions with Jupiter and other satellites. You have resonances, and those resonances tend to pump energy into the satellite.
Locked in a constant tug of war, tremendous forces constantly push and pull the moon so that it is kept at a constant boil. Even as such, Io does have a bit of an atmosphere, composed mainly of sulfur dioxide, the same stuff that you can find in the atmosphere of Venus. While poisonous to man, it does serve to shield the moon's surface from the intense barrage of charged particles raining down from Jupiter. Man could land on Io, but he probably wouldn't stay too long. Ganymede is the largest of Jupiter's moons. At 3,275 miles in diameter, it is bigger than the planets Mercury and Pluto. It is believed that Ganymede has a thin atmosphere comprised of oxygen and water vapor. If this is the case, then the possibility of human habitation will be greatly enhanced. This moon, however, does not appear to have anywhere near the internal heat that Europa has. Therefore, its surface of mixed rock and water ice appears to be solid through and through. Life may have evolved here in an earlier time, but the chances of finding it now are exceedingly slim. Callisto is the 2nd largest of the Jovian moons, and is composed of mostly rock and water ice. It is the most heavily cratered satellite in the system, and as such, it serves as an indication that the other 3 moons must have very active cores in order to have managed to obliterate the great majority of their impact craters. Much can be gained by the study of Jupiter and its moons, and such study can begin with the Galileo project scheduled to arrive in the Jovian system in the mid-1990s.
probe comes in two parts, an orbiting pickup satellite and a smaller lander, which will be separated from the orbiter and dropped into the atmosphere. There it will radio back its analysis of the gas clouds it will encounter, doing so until it is crushed by the intense pressure within the deepest regions of the planet. Before it perishes, however, it will provide us with the first detailed atmospheric analysis of the largest planet in the solar system.
And Everyman's Guide to the Planets will continue on TLC. And Everyman's Guide to the Planets now continues on TLC.
Saturn is the second largest planet in the solar system and the sixth planet from the sun. Despite its immense size, its mean density is less than that of water. Clearly, Saturn is made up of very light stuff indeed. It cannot be much more than a giant gas bag mixture of hydrogen and helium. Saturn is the best known to us because of its prominent ring structure, a structure first observed and reported by Galileo in 1610. It was some time later when scientists deduced the true nature of the rings. Before the 19th century, it was believed that the rings of Saturn were part of the planet, a solid mass, like a halo, if you will, that was connected to the planet's surface. It was presumed by some early astronomers that life must exist on such a grand place. Well, we know now exactly what the rings are. They are essentially small chunks of water ice that circle the planet upon a single orbital plane. While it is 250,000 miles wide, it is only a few yards thick. The ring system is obviously either the remnants of matter which combined to form the planet some 5 billion years ago, or what is left over from the breakup of a very large orbiting satellite. Seen close up by the Voyager spacecraft, the rings reveal an incredible intricacy. The clumps of ice move in cascading waves and form exquisite symmetrical patterns.
Well, Saturn, of course, has been known as the ring planet ever since people first started looking at it with telescopes back in the 17th century. Saturn's rings are by far and away the most beautiful and prominent ring system. They're the only ones you can see easily from ground-based telescopes, for instance. I think one of the most exciting things anybody has ever done in their astronomical career is their first look at Saturn through a really big telescope. It's really, really mind-blowing.
The interior of Saturn is most certainly made up of hydrogen in a liquid state, and more exotically, at the deeper regions, liquid metallic hydrogen, formed when the increasing pressures force electrons off of the hydrogen atoms, thereby forming a metal. This metal may make up the core of Saturn, or we could have another planet-sized diamond. Nothing is certain yet.
Saturn itself is something like 2/3 to 3/4 of a Jupiter. It's a large liquid gas planet, very similar in Jupiter in its overall composition, but displaying different types of atmospheric features which are quite interesting.
As is Jupiter, Saturn could be said to be a star that failed. However, the failure was much more pathetic in the Saturnian case, as it would require that the planet be hundreds of times more massive in order to become a star, rather than the mere 10 of Jupiter. Saturn has the most extensive satellite system of all the planets, and also possesses the second largest moon of all, the giant Titan. At over 3,100 miles in diameter, Titan is larger than the planets Mercury or Pluto, and has a considerable atmosphere as well. an atmosphere comprised mainly of nitrogen. Up until recent times, it was presumed that Earth was the only place in the solar system where nitrogen was predominant. Now we see that Saturn's moon not only has a nitrogen atmosphere, but it is 60% denser than our own. Beneath a haze of cloud cover, complex chemical reactions take place which form the main components of Titan. Though it has an upper atmosphere similar to ours, the extreme cold temperatures prohibit the development of any kind of life similar to our own. After all, Titan is about 10 times farther from the sun than we are. Yet Titan could turn out to be a most fascinating place.
In the Saturn system, there are several very interesting bodies with respect to this. One of them is Titan. It's been known to have an atmosphere since 1948 when Gerard Kuiper discovered it. And that atmosphere is primarily nitrogen. It's the first really massive nitrogen atmosphere we've found any place in the solar system other than the Earth. It has a surface pressure about 1.5 times the surface pressure at the Earth. Nitrogen atmosphere, methane in the atmosphere. The methane at the upper layers of the atmosphere is subjected to radiation from the solar ultraviolet rays and from particles from the radiation belts of Saturn, and organic synthesis takes place. You'd think this is a great place for developing life.
You see, the temperature on Titan is estimated to be about the triple point of methane, what we call natural gas. That means that the temperature is such that with minor variations up or down, methane can go from being a gas to a liquid and then to a solid. This is the case on Earth, where water can exist as steam, then cool to become liquid, and within a few degrees freeze to solid ice. That would mean that on Titan it probably rains liquid methane into a sea or river of liquid methane, and in the northern and southern poles it snows methane crystals onto glaciers made up of methane ice. One other satellite of Saturn bears some observation, and that is Enceladus. Enceladus is very similar to Europa in many ways, in that it seems to have its own internal source of heat. This heat serves to melt the lower levels of ice on the moon into a slushy liquid, and at greater depths, this liquid may reach temperatures capable of sustaining life.
As a surface, it's very similar in its appearance in some ways to the surface of Europa. It has very smooth areas on it. It's obviously been resurfaced. There are areas that have very few meteoroid craters on them. We don't know for sure where that energy is coming from. Just radioactive heating is very hard to, it's very hard with just radioactive heating to produce enough heat to melt an object that small. We think it may be, again, akin to Io and Europa in getting tidal energy from Saturn, although theoreticians have not been able to come up with quite enough energy to do the job. Nature has obviously figured out how to do it, and Enceladus is a very interesting place and might tell us a lot about these energy sources.
The surface is remarkably free of craters and other evidence of geologic activity. This primarily is due to the continuous motion and regeneration of its ice crust from upwelling liquid water currents. At 310 miles in diameter, Enceladus could potentially be the smallest dwelling of possible life in the solar system. Perhaps because they are the biggest and most colorful of the outer planets, Jupiter and Saturn receive much of our attention. But being relatively close to us is advantageous as well. Jupiter and Saturn can both be seen and studied by everything from mountain observatories to backyard telescopes. Together, through their moons, they offer a tremendous sample of the variety of worlds available for our exploration in the future. One thing stands clear. If we are to find a place for ourselves in the outer solar system, it will be near one of the two stars that failed. planet Uranus was discovered almost accidentally by a then amateur astronomer named William Herschel in 1781. Uranus has remained a mystery ever since. Millions of bits of data were collected at the Jet Propulsion Laboratory from Voyager's encounter with the planet. And this data has revealed some amazing secrets of the most bizarre planet in our solar system. Uranus is interesting to astronomers for many reasons. The first and most obvious is that the planet is tilted on its side. That is, its south pole faces the sun rather than its equator. This can be clearly seen by the position of the delicate Uranian ring structure. Why Uranus is tilted over 90 degrees on its axis, no one knows for certain, though it appears that during the early formation of the planets, Uranus must have had a catastrophic collision with an object at least planet-sized, which caused it to tilt so violently. Ejecta from this collision probably formed the 5 large satellites that orbit the planet, as well as the 10 smaller moons and the ring structure as well. Uranus lies 2 billion miles away from the Earth, and as such, light falling on the planet from the sun is extremely dim.
Voyager was built to go by Jupiter and Saturn. It was put on a trajectory that would take it by the outer planets, but without the funding to ensure that the mission would go on that long. And the spacecraft itself was only designed to go by Jupiter and Saturn. What that means is that we have an infrared detector and the cameras, which are really straining out in this cold, dark environment to get data. And what that means is that we have to do what's called image motion compensation. We track our target so that while the shutters are open on the cameras, we are tracking what we're trying to take the picture of.
Uranus is about 4 times the size of Earth. It also appears that the 7th planet from the Sun has a rocky core about the size of Earth that is surrounded by a sea of liquid water, a sea totally unlike anything with which we are familiar on Earth. This ocean, which is larger than the entire planet Earth, is compressed so much by the forces of gravity that it actually becomes electrically conductive. That is, it generates its own electrical fields. At the higher regions, where the water is frozen into ice, it is so cold that the ice is as hard as steel. This ocean produces 2 interesting features of Uranus. The first is a strange magnetic field which rotates in a highly irregular orbit about the planet. And this magnetic field, in turn, creates what scientists call electroglow. Uranus sits in space with an eerie, nebulous glow surrounding the entire sphere.
We know one thing, its magnetic field is very strange. Instead of being aligned more or less with the spin direction of the planet, as most of the other magnetic fields we've seen in the solar system are, it's tilted by 56 degrees, 59 degrees, almost 60 degrees, meaning that as the planet rotates this way, the magnetic field goes around like this. And there are a lot of theories just being developed now based on the Voyager data as to what's going on here. One possibility is that this magnetic field is in the process of changing its polarity, as the Earth's field does every few thousand to 10,000 years. And we just happen to catch it in an unusual state.
Even though the sun is always shining on the south pole of the planet, the temperature of its atmosphere is constant from north to south. It has huge weather systems, much like Jupiter and Saturn, though they are harder to photograph due in part to the fact that the atmosphere of Uranus is comprised mostly of methane and ammonia, which reflect light in a very similar fashion. Then there is Neptune. Very little is actually known about the 8th planet. Orbiting 30 times farther than the Earth from the Sun, Neptune is most certainly a very cold place.
We knew very little about Neptune's atmosphere just a few years ago. We're now learning that it's a very active atmosphere, much like Jupiter's atmosphere. It has bands, has bright bands, dark bands, it has bright clouds and dark clouds. And Neptune's atmosphere is very exciting because it changes all the time. Every rotation you look, you'll have a different cloud feature will appear, and the features that were there previously are gone. And that's something that we've seen on Jupiter, for example. The clouds there are very dynamic and they change all the time. Neptune has a very thick atmosphere. You couldn't breathe it. You couldn't go and land on that atmosphere. You couldn't land on the planet. It's like Jupiter in that the atmosphere is very, very thick. So thick that it gets heavier and heavier until it turns into basically a liquid state. There's no surface that you could stand on and say, okay, I'm standing on Neptune. You can't do that on Neptune.
It is almost exactly the same size as Uranus, though it is not tipped on its side. Its orbital axis is a relatively calm 28 degrees. The analysis of Neptune has shown that it is made up of a solid core of rock and water ice, but there appears to be evidence of methane ice as well. This would indicate that the temperature of the planet is some 200 degrees below zero. Nonetheless, the measured radiation from the planet is greater than that which can be accounted for by the meager amount of sunlight that strikes it. That is, Neptune, mysteriously, is giving off more heat than it is receiving from the sun. Even amidst temperatures cold enough to freeze natural gas into blocks of ice, some process is taking place which generates heat. No one is yet quite sure what it is.
We're not sure why Neptune's atmosphere radiates more heat than it gets from the sun. Maybe a better question to ask is why Uranus doesn't have an internal heat source, because all the major planets that we work with, Jupiter and Saturn, both have internal heat sources, and Neptune. So 3 out of our 4 major planets do have internal heat sources. Uranus, without one, is really the oddball, not Neptune for having one. And that heat source comes from a number of things. It comes from the gravitational contraction of the planet when it was originally formed. As you have a lot of material and mass in the primitive solar nebula before we had planets, as this mass contracted to form the planet, the contraction released energy, and the energy is still stored up in the planet as it's forming. And the planet that we have now still has residual energy left over. And that is a part of its internal energy source.
Neptune's atmosphere is much more dynamic than scientists had imagined. There appears a huge storm in the atmosphere, very similar to Jupiter's Great Red Spot, and as such has been appropriately dubbed the Great Dark Spot. Above and below this storm, there are numerous small white clouds which travel with and against the wind current, which have been called scooters. As Neptune is the most recently visited planet, and in fact the last planet on Voyager's tour, scientists at the Jet Propulsion Laboratory will be sifting through billions of bits of data over the next 100 years to discover the true nature of the last giant planet of our solar system. This much can be said for Neptune. It possesses 2 large satellites, Triton, which is about 2,000 miles in diameter and is coated with methane ice, and Nereid, which is barely larger than an asteroid at 185 miles in diameter. Triton, obviously the larger of the 2, is also the most fascinating. Its orbit is completely opposite that of the rotation of Neptune. As it passes very close, come ever closer to the surface.
One interesting thing about Triton is that, well, you probably know that in the case of the Earth's moon is very slowly spiraling out away from the Earth. In the case of Triton, the planet and the moon are going in different rotational directions, and so it's ever so slowly spiraling in.
Eventually, Triton will slow to a point where its centrifugal force will be insufficient to retain it in orbit, and then it will begin its catastrophic fall into the very heart of Neptune. No one is quite sure what effect a huge body such as Triton will have falling into a planet as large as Neptune, but most assuredly, it will be quite a spectacle to witness.
And Everyman's Guide to the Planets will continue on TLC. And Everyman's Guide to the Planets now continues on TLC.
With the discovery of Uranus, mathematics was utilized to hypothesize the location of the 8th planet, Neptune. Amazingly, it was calculated and predicted to be in almost its exact position. From there, the mathematicians began to calculate again. and advanced theories of where the 9th planet should be. One man, Percival Lowell, relying on faulty data, predicted the location of Planet X and estimated that it would be very large. Lowell never found Planet X, but the search continued. In 1928, a young astronomer named Clyde Tombaugh, after months of painstaking observation and analysis, found Planet X, amazingly close to where Lowell said it would be. The planet was named Pluto, after the god of hell. It is interesting to note, however, that the first 2 letters of the name are Percival Lowell's initials.
The imaginary picture would probably be like a cratered surface on Pluto due to impacts, but white due to the frozen methane frost on the surface, making it rather highly reflective. And of course, with the craters and all, and then there'd be Pluto's moon up in the sky, if you're on that side of Pluto, because it makes the same period of revolution as the rotation of Pluto.
Pluto turns out to be much smaller than Lowell predicted, and too small to cause any significant deviations in the orbit of Neptune. In fact, Pluto is so small that many believe that it shouldn't be called a planet at all. Its diameter is only 1,500 miles, about 1/2 that of our moon, and that it is made up mostly of methane ice with a little rock thrown in for good measure. Pluto does have a satellite, though, so it has managed to hold its rank as a planet thus far. The satellite is called Charon and wasn't found until 1978. Charon is about 475 miles in diameter and orbits Pluto once every 6.4 days, matching exactly the rotation of its parent, so that on Pluto, the moon is always in the same spot in the sky, and the sun, shining dimly like a distant star, lies some 3 billion kilometers away.
After Neptune, Voyager will just head on out of the solar system. It would take too much energy, too much fuel to turn around and bring it back. And I don't think we want to. I'm really kind of proud to be one of the generation that has sent something away from the Earth, never to return. I mean, who knows where it's going to be billions of years from now, but it's a little piece of our generation, our culture, that's just out there leaving. And maybe it's the first step of mankind out from our solar system. And I think that's exciting.
And Everyman's Guide to the Planets will continue on TLC. And Everyman's Guide to the Planets now continues on TLC.
It is unlikely that we will take the time to explore Pluto and Charon. Simply too far away and much too cold for us. And so where do we go from here? To what end do we continue to explore the planets?
We as a civilization are getting big enough that we can and are affecting our own planet. And some of those effects are not very good. We need to understand how a planet works, what it does when you touch it, what it does when you heat it, what it does when you cool it. And in order to do that, we have to have more than just earthly data. We have to have enough data about our sister planet Venus and our sister planet Mars and the other planets to understand how this generic planet works. If we don't do that, then we face a possible extinction of the species. And I can't think of a more important reason to do anything.
A lot of times people ask me, what good is it that what you're doing? I mean, why bother studying Neptune or the outer planets? I mean, what do they tell you about Earth here? You know, we have a lot of problems here on Earth. Why study all that stuff out there? And there's two things you can answer. One is the technology question, all right? By studying another planet's atmosphere, we can learn about our atmosphere. We can learn about chlorofluorocarbons, CFCs, and why we shouldn't have aerosol hairspray. You know, by studying chemistry of other planets, we learn more about the chemistry of our planet, and that's an important thing. Aside from those kinds of questions, though, there's the broader question of knowledge. I mean, what's man's purpose? It's to learn, to grow, to expand. And studying our closest neighbors in the universe, the other planets, is, I personally think, an important first step for understanding the universe.
Of all, the most compelling reason is to gain a better understanding of our own Earth. For the other 8 planets and their moons offers an excellent sample of the diversity of environments and geologic evolutions that take place in the solar system. In some instances, their study provides us with details of what could go wrong with our own planet. And then there is the search for life. So far, everything we have encountered besides Earth, this lonely corner of the universe, is dead. Either it is ice or rock or gas, but it is not alive. Now, we do know of places where there may be life, or at least the potential is there. We must look and see. "64 million years ago, an entire class of living organisms perished upon this planet, never to be seen again, because they lacked the ability to foresee changes in the environment in which they lived. And as such, they were unable to adapt when the need arose. Now this is a trilobite, a marine animal that lived on the Earth tens of millions of years ago. It and the dinosaurs are gone. Only these fossilized remains are here for us to see. This beach is full of remnants of creatures who have gone before us. Once they were masters of the globe. Once. Now, we must not be like the dinosaurs. We must investigate any and all possibilities of life elsewhere to see how that life adapted to its own unique set of environmental pressures in order to assure that we can survive any changes to our planet. We must also look for other places to live, to explore. Man is not by nature a sedentary creature. We've always been nomads, traveling the world, journeying into uncharted territory, creating a place for ourselves to live and grow, regardless of the odds. There are very few challenges for exploration left on our home planet. Space and the other planets in our solar system are clearly in our future. But wherever our travels take us, we should always remember the Earth. So this is the planet that gave us birth, cared for us, and gave us the ability to dream. And dream we must, for it is only by holding on firmly to our dreams that we can truly reach for the stars.
For the fiery world between us and the sun, as we continue touring the cosmos with an Everyman's Guide to the Planets, next on TLC.
Man has gazed with wonder, staring at the mysterious points of light and luminous moon as they cross the heavens, made him consider his own existence, and formed within him a basic curiosity of life that is still with us today. These shiny, bright dots in the sky were beyond early man's experience. He could not feel them, hold them, taste them, or even see them very clearly. The stars must be the eyes of God, he thought, or diamonds that shone through the dark shell of night. And the moon must have been a servant sent by God, a servant that alternately comforted him, controlled him, and at times tormented him at will.
This huge sky, virtually misunderstood by mankind, instilled fear in many early societies. It was said, and is still believed today, that the movements of the stars controlled our destinies. Such is the philosophy of the pseudoscience known as astrology. Ancient peoples, having been successful on a given hunt, let's say, were told to thank their lucky stars and so forth. As civilization progressed, so did man's thirst for knowledge of the universe above him. Stars began to be classified into groups known as constellations. And later, those stars that were observed wandering across the sky in set patterns were dubbed planets, which quite literally means wandering stars. And as these planets were discovered, they were given names, generally chosen from Greek or Roman mythology.
Mercury, the messenger of the gods, the closest planet to the sun and one of the smallest. Venus, the goddess of beauty, the second planet from the sun, tropical paradise. Mars, the god of war, the fourth planet from the sun, known as the red planet, its color clearly visible from Earth. Mars is very similar to Earth, and at one point in its history had flowing rivers of water running across its surface. Jupiter, named after the most powerful Roman god, is the fifth farthest planet from the sun. But it is by far the largest, being equal to the mass of 1,000 planets the size of Earth. Saturn, the sixth planet, orbits the sun only once every 29 years. Hence, the ancients named it after Kronos, the god of time. When people think of a planet besides Earth, they most often think of Saturn, due to its extensive ring structure made up of billions of chunks of ice and rock. Uranus, named for Urania, the mythical Greek astronomer, was unknown to ancient man. Too far distant from the Earth to be seen with the naked eye, the seventh planet from the sun has proven to be one of the oddest, in that many of its attributes seem to contradict known laws of physics and motion. It possesses a ring system much like Saturn, but it is less spectacular. Neptune, named for the Greek god of the sea, is very much still shrouded in mystery. Undiscovered until 1846, Neptune, like Uranus, is made up almost entirely of liquid gases and ice, with the possibility of a solid core. Its bluish-green color is due to the high amounts of methane gas in its atmosphere. The farthest planet from the sun was not discovered until 1930 by a young astronomer named Clyde Tombaugh. It is by far the smallest of the planets, only about 800 miles across, and is composed mostly of methane ice. It is so far away that the sun appears as no more than a merely bright star when viewed from the planet's surface. As cold as deep space can be, Pluto is appropriately named after the god of the underworld, the god of an ice-cold hell 3 billion kilometers from the sun.
You see, it's very simple, as are many things that are seemingly difficult to comprehend. The position of the stars in the Milky Way are relatively constant to one another. In actuality, they, like our own sun, are orbiting the center of the galaxy. But as it takes 200 million years for one such orbit, it can be said that in our short span of observation, they barely move a whisker. Anyway, once the ancient mariners had determined the position of the stars in the sky and accurately cataloged them, they were able to determine to a fair degree their own position on the Earth by simply looking up in the sky and gauging the change of the stars' so-called fixed positions. But what does all this have to do with the planets? To understand our curiosity and our unceasing study of the planets, we must look to how mankind utilized his knowledge of the motions of the bodies above him. For in many ways, by studying the planets, we can glimpse not only into our Earth's past, but maybe its future as well.
Space travel, though commenced just in the last 30 years, is not a new idea. In fact, Johannes Kepler wrote in a work entitled Somnium of a trip to the moon, and he did so in 1634. Interestingly, Kepler's hero used demons to translate, which to Kepler was remarkably similar to Earth, only that it was ruled by barbarians. Unlike modern times, grandiose ideas of this sort were not immediately put into practical operation. It took 300 years for man to develop the machines that would take him into space. Though we found no barbarians on the moon, in many ways our advances in the technology to achieve spaceflight arose from civilization's conflicts with barbarians of its own making. Most notably, Adolf Hitler and World War II. By the start of World War II, modern design rockets had already been developed and tested. In fact, the first launch of a liquid-fueled rocket had taken place on March 16, 1926. An American scientist, Robert Goddard, was the first man to create a rocket capable of sustained, controlled flight. Of course, this first rocket streaked into the sky for a total flight time of 2½ seconds. But it was a start. But the German government during the war undertook one of the most impressive technological development programs in history, all with one purpose: the creation of sophisticated weaponry to ensure German domination of the entire European continent, if not the world. Among such advances as the jet aircraft, the German scientists invented the infamous V-2 rocket, which they utilized to rain down destruction on the whole of England until the defeat of Germany in 19... However, before succumbing to a monumental concerted effort on the part of the Western Alliance, they managed to design and build a two-stage liquid-propelled rocket, the precursor of our own modern-day launch vehicles. The defeat of Germany and Japan in World War II left the United States as the world's most dominant power, and hence the country best suited to further development of rocket technology. The first rockets developed for spaceflight suffered many fatal flaws and were doomed to destruction on the launch pads. This happened time and time again until significant problems in design and quality control were worked out and the United States space program began in earnest. Like the ancient mariners who set sail for uncharted and undiscovered lands, we too have sent our own mechanical missionaries into the outer reaches of the space frontier. So far, one of those missionaries, Voyager 1, has left the known solar system and now flies at 35,000 miles per hour into deep space. It carries on it a message from its maker to anyone who may come years ahead. Its message is encoded into a gold record which says very simply, "Hello, this is who we are, this is where we are from, and this is what we sound like." Imagine an intelligent life form billions of years from now believing, as many of our species do, that life only occurred on his planet in his solar system, coming across this obvious and literate example of a life form from a place light years away. He will know then that he is not alone. The closest planet to the Sun, Mercury, understandably possesses one of the harshest and most variable environments. Hot enough to melt lead and boil sulfur during its long day, then as cold as space itself at night. Viewed from the planet's surface, the Sun would be a huge boiling mass that fills 2/3 of the sky. Of course, while one might stand on the surface of Mercury, at least the night side, should you do so during the day, you would be reduced to a pile of ashes within seconds. Not a very nice place.
Because Mercury has no atmosphere, things are very different there. We find enormous differences in day and nighttime temperature. And for us human beings, the problem is that it's always either too hot or too cold. So the place where human beings would probably start to explore Mercury would be in the twilight zone, in the zone between day and night.
A little more than 1/3 the size of Earth, Mercury nonetheless is a rather heavy planet. Its composition is very similar to Earth's, in that both have a core that is made up of iron. Mercury is in a virtual vacuum. There is no atmosphere surrounding the planet whatsoever. A planet this small has a rather difficult time holding on to any kind of atmosphere due to its low gravity. The air just floats away out into space.
The big thing that we don't know about Mercury is that we don't know whether there's a lot of volcanism there or not. I mean, what we see on Mercury is we see craters and we see intercrater plains. Now, it may be that those intercrater plains are volcanic, but that's about all you can say mineralogically.
But there is a second reason for Mercury's emptiness, the heat. Any gases present in the early history of its formation have long since boiled off by now. Whatever gas was present in Mercury's interior rocks is now far off into space. Perhaps some of it has floated into the path of the Earth to be inhaled by some living creature, maybe one of us, breathing deep that single molecule of hydrogen that escaped from such a lonely place billions of years ago. Mercury looks very similar to the Moon in that it is extremely pockmarked by craters that have not eroded away. Huge valleys and mountain ranges on the surface seem to indicate that at one time Mercury was alive with volcanoes, much as Earth was, except that evidence shows that the core of Mercury has cooled down now to a mostly solid mass. As it does so, it becomes denser and smaller. Thus, Mercury, the second smallest planet in our solar system, is gradually shrinking. Imagine, if you will, a planet that circles the sun once every 88 days. A planet whose surface temperature during the day is over 900 degrees, and at night to some 400 degrees below zero. A planet where salt and lead would boil away during the day, and where the breath you exhale would freeze into ice at night. This is the forbidding harshness of the closest planet to the sun. This is a day in the life of Mercury. Well, the truth has been discovered about Venus, beaming up detailed information of the planet's atmosphere during the slow descent. In 1975, the Soviet Union, after previous mixed success in landing a probe on Venus, launched the Venera 9 and 10 spacecraft. Designed to land on the surface, they were packed with scientific instruments to measure and analyze the atmosphere, record temperatures, atmospheric pressures, and equipped with 2 cameras to radio back the first pictures from the surface of the planet. What the Venera landers discovered upon their entry into the atmosphere laid to rest any hope of finding life as we know it on Venus. Mist-like clouds of acid, sulfuric acid to be precise.
The atmosphere is very corrosive, I'm sure. The atmosphere on Venus mostly consists of carbon dioxide with sulfuric acid. Well, I mean, we all know that sulfuric acid is not particularly healthy for living beings. Carbon dioxide is not too bad, except there's no oxygen. And so the lack of oxygen would be another thing that you'd have to deal with.
Beneath this stinging layer of acid clouds lies a lower atmosphere made up principally of carbon dioxide and nitrogen, what we commonly call smog, but without any oxygen. As the Venera landers descended further, they began recording both higher temperatures and higher pressures, ever increasing, in fact, until at the surface, a pressure of over 1,300 pounds per square inch is exerted upon everything at a temperature of over 900 degrees Fahrenheit.
Of all the planets that we've been to, Venus is probably the least hospitable. Now, that's due primarily to 2 things, the temperature and the pressure. The pressure is about 100 times the pressure on Earth, and the temperature is as high as 700 degrees Fahrenheit. So to stand on Venus and to look around would be very difficult for a human being to last very long. When the Soviet probes landed on Venus, they didn't last very long either. If you look at a picture of what the Soviet probes look like, you can tell what they were designed to protect against. They look like huge boilers. A boiler is built to contain pressure. The boilers that the Soviets sent to Venus were built to resist it. And what 90% probability made these landers fail when they did was the extreme pressure and the extreme temperature.
There is a very important reason for us to study the environment on Venus. It is far and away the best, or possibly the worst, example of what has been termed the runaway greenhouse effect. The theory behind it is very simple, but has drastic implications for the Earth and life as we know it.
All planets are to some degree heated by the sun. This heat radiation is called infrared. It is the same radiation that comes from electric heaters, toasters, and our bodies. Some of the sunlight that strikes a planet is reflected off of the atmosphere and back out into space. Some is absorbed by the atmosphere, and some is transmitted to the ground. On the ground, the sunlight warms the rocks and dirt, which release heat or infrared radiation. Once again, some of this is absorbed by the atmosphere, some is reflected back to the ground, and some is transmitted back into space.
On Earth, this works in total harmony. Just enough sunlight is absorbed by the ground to maintain temperatures in which all living organisms can survive. The rest is reflected back up into space. The exact same thing occurs on all planets with atmospheres to one degree or another. Now that is where we start to make comparisons between the Earth and Venus. Our planet contains virtually the same amount of carbon dioxide as Venus, except that 90% of the CO2 is still found in the crust of the Earth, whereas on Venus, almost in the atmosphere. Another related issue on our own planet, equally important as the runaway greenhouse effect, is the protection of our safeguard, if you will, known as the ozone layer. The Earth possesses a layer of ozone in its outer atmosphere that effectively blocks the majority of ultraviolet radiation that would normally pass through to the surface. This keeps the plants and animals from being fried to death. And because it keeps plants alive, they continue to absorb sunlight. This keeps Earth relatively warm. And maintaining planet warmth is equally important to keeping it cool. Another ice age could be devastating to our species. But in the last few years, a dramatic change has been noted in this ozone layer. It seems as though a hole has appeared in the ozone layer above Antarctica. This hole fluctuates in size, but it has become increasingly larger as the years have progressed. Should this layer of ozone dissipate, life on this planet would surely meet a very dismal end. A theory has been proposed as explanation for this phenomenon, and it involves the widespread use of aerosols in our society, most notably chlorofluorocarbons, often known by the trade name Freon.
Freon is used in countless applications in our society. It's in freezers. It cools our offices and cars. It propels our antiperspirants and hairspray. An agent which is known to destroy ozone, that remarkable layer which enables our lives to continue. And on the other hand, we continue to burn fossil fuels in our factories and our automobiles, the exhaust of which is primarily CO2. Not only are we contributing to an increase of the surface temperature, which results in more carbon dioxide being released from the rocks, but we are directly adding CO2 to the atmosphere as well. Where will it end? As yet, no one knows.
One thing remains clear. Our environment on this planet is very tenuous indeed. Should a greenhouse effect get started on Earth, there is no way we could stop it. Within a few thousand years, the temperature and pressure on the surface would become so oppressive that all life would end. Now, as the most intelligent creatures on this planet, it is our duty to see to it that that does not happen. To a point, we are truly masters of the Earth's destiny. To a point.